Hello. It is very important for every mechanical engineering design to be aware of the reliability of the mechanical component to be manufactured and become a product in the market. And in the process, it's important to understand the distribution of stress and strength and their probability to keep an acceptable distribution of interference. So what is the probability of failure? Simply it is how likely a failure is to occur. And in order to express those probability of failures, it's better to use the probability distribution over several events. And the probability distribution, the probability density function expressed in this figure A, will give us an understanding of events, several events, in a given range of values. And we notice that the total probability of all events, which is the area under this curve, must be 100% or equal to 1. There are different types of distributions. In this example, because this function is symmetrical with respect to the mean, and we see that there is a standard deviation around the mean, which is symmetrical, then the equation of f of x can be easily derived, and it is known as the Gaussian distribution or normal distribution. This is only one type. I mean, there are like Weibull distribution and many other distributions. But this type is called the Gaussian or normal distribution, at which the figure or the function has a bell-shaped curve. Okay, distribution. And we notice that it is dependent on the mean and the standard deviation. So the function f of x is equal to 1 over standard deviation 2 pi. Okay, we will put a head over the standard deviation just to distinguish it from the stress. Exponential minus half of x minus the mean over the standard deviation squared. Okay. The difference between figure A and figure B is only in the standard deviation, and a low value of standard deviation, I mean how the values are distributed around the mean, okay, gives the following figure if the standard deviation is with a small value. If it is with large value, we see such kind of curve. Now, if we are asked to find the probability, for instance, let's take an example, for x less than, let's say 18, okay, then it is the area, x less than 18, it is the area under this part of the curve. It's from minus infinity till 18. So the probability of x less than 18 is the area under the curve, which is the integral from minus infinity till 18 f of x dx. However, it's easier to use tables in such type of integrations. It's make our life easier and things much faster. However, because there are different scenarios and different experimentation with the different data have different values of standard deviation and mean, and thus in order to avoid to have too many tables for each scenario, what we are going to do is to normalize the value by subtract it from the mean and dividing it by the standard deviation. So the values will become standardized, at which we can rely on only one table if we take off the mean and the standard deviation. and this is called the z-score, okay, or z-transformation. And this can be done by converting the data x by subtracting the mean and dividing it by the standard deviation. Okay, so the new equation of the probability will become in this form. So because we subtracted the mean and divided by standard deviation, we can find a table at which we can obtain the probability very easily, at which if we have z is negative, the probability will be alpha. So if we are saying, let's say, the probability of z less than 0 minus 0.1, okay, we can just look over 0.1, 0, and this is negative, then it is equal to alpha, okay, which is 0.4602. If we say we want to obtain the probability of x less than 0.1, 0.1 is positive, z is positive, so we need to put 1 minus alpha, so 1 minus 0.4602, okay. And each value on this table, the probability provided here in the table, represents for z less than, so to the left side of the curve, okay. So if we want to draw the curve, so those probabilities represents for the values less than a certain value of z, okay, probability of z less than, okay, this must be z because we are using the z value, okay. This is the another part from the table. Let's take an example. If x is the normally distributed variable with a mean of 11 and a standard deviation of 5, and we are asked to find the probability of x greater than 21. So again, it is greater than 21. We can use the integration from 21 to plus infinity of f of x dx. Okay, but it's easier to use the table. So we do not integrate in this course. We use the table, which are derived numerically. So the first step is to normalize this value of x in order to use this table, the above table. So we say z is equal to 21 minus the mean over standard deviation, which is equal to 2. Okay, and we notice that if we want the value for greater than 21, okay, and we know that the table only provides r for x less than 21, okay, it provides us this area less than 21, from minus infinity to 21, okay. So this can be obtained from the table, and we know that the total probability is 1. So in order to obtain the probability of x less than greater than 21, it's simply you can subtract the total probability 1 minus this red region, okay, this one from the table. You can obtain the greater than 21. So the probability of x greater than 21 can be normalized as z greater than 2, which is equal to 1, the total probability, minus the probability of z less than 2. Okay, now we want to obtain this probability from the table. It is 2.0, which is 0.0228. Okay, And remember, z is positive, so we need to subtract 1. 1 minus the value on the table. Okay, so it is 1 minus, so for probability z less than 2, it is 2 is positive, so we need to say 1 minus 0.0228. So we can plug it here. 1 minus 0.0228. Okay, which is equal to 0.0228. Another example. We are asked to find the probability of x between 13 and 23. So the first step, we normalize each of those values to use the table. So Z1 is equal to 13 minus the mean over standard deviation, which is 4. Okay, this is 0. And Z of 23, the second one, 23 minus 13 over 4, it is 2.5. Then the probability becomes between 0 and z square 2.5. Now we want to obtain between 0 at 2.5. We want to obtain this area. The probability is the integral, right? Between 0 and 2.5. And the table provides us only for z less than 0 and z less than 25. So this is 0. Okay. It provides us this area, z less than 0 and z less than 22.5. Okay, this one. So in order to obtain this red region, okay, simply we can subtract this one from this one and we can get the overlap. Okay, so it is the probability. This is the probability of z less than 2.5. We can subtract it from the probability of z less than 0. We can obtain this shaded region in red. So probability of z less than 2.5 minus the probability of z less than 0. This is equal to this area. Okay, all of this. Now this is positive 2.5. 1 minus, we can obtain the alpha from the table. Again, if z is positive, we need to say 1 minus alpha. 2.5, okay, 0, 2.500, okay, it is 0.00621. Probability of 0, okay, it is 0.5. 0.5, and the value is equal to 0.4938. So I hope now it's very clear how to use the z transformation table or z score table. Let's take another example. In a shipment of, we have 250 roads, connecting roads. The mean tensile strength is given as 315 megapascal, and the standard deviation is given as 35 megapascal. Now assume that this scenario is normally distributed. How many roads can be expected to have a strength of less than, so we need to obtain the probability that a certain road has a probability of X less than 276.5 megapascal. Okay, the strength is less than 276.5. Okay, again, we normalize this value. Z is equal to 276.5 minus 315 over 35, which is equal to minus 1.1. Okay, so this is the probability of Z less than minus 1.1. We notice that Z is negative, and if it is negative, we choose the value exactly as it is in the table. 1.1, it is 0.1357. 1357. Okay, and this is the same as 13.567%. I mean 13%, 13.5% of the roads will have a probability of less than a strength less than 276. Then the total number of roads will be 13. Okay, the number of roads with strength less than 276.5 megapascal is equal to 13% of the 250. So 13, or we can use directly this one, 0.1357, which 13% multiplied by the number of roads, 250. This is equal to 13.5. I'm sorry, 33.9 roads, which is approximately 34 roads. So 34 roads will have a probability that their strength is less than 276 megapascal. Part B, how many are expected to have a strength between, so this is part A, part B, probability between 276.5 and 1416.5. So this is the probability of X less than 14.16.5 minus probability of X less than 276.5. Okay, we normalize those values. So Z is equal to 14.16.5 minus 315 over 35, which is equal to 2.9. So this is equal to 0.9. So this is the probability of Z less than 2.9 minus the probability of Z less than minus 1.1. Okay, again this is Z is positive. Remember, we should say 1 minus alpha. Okay, 1 minus the probability of 2.9 is 0.0087. Okay, minus the probability of Z less than is minus 1.1 is obtained in part A, and this must be equal to 0.8624, which is approximately 86.2%. So 86% of the roads will have a strength between this value and this value. So in order to convert this percentage into number of roads, we multiply by the total number of roads. Okay, so the number of roads with a strength between 276 and 416 is 250 roads multiplied by this percentage, 0.86243, which is equal to approximately 216 roads. Okay, so we have 216 roads with a strength between 276 and 416 megapascal. Okay, and now in real life scenario, once you go to the laboratory, you will be collecting the data, and it's your responsibility to determine the mean and the standard deviation, and I assume they must be easy for you to calculate. So in order to calculate the mean, you just sum all the data you have and divide by the number of data you collected, and this is equal, the average is equal to 1 over n, the total number, fi xi, how frequently each value is repeated, you multiply it by x. So let's assume you have grades of 4 students, and you got 18 over 20, 17, 18 over 20, and 15. Those are the grades of the students. So you can put them in a table. The grade, you have 15, you have frequency, 1 student got 15, 17 you got 1 student, 18 you got 2 students. In order to find the average of the grade inside the classroom, you just say xi 15 multiplied by 1 plus 17 multiplied by 1 plus 18 multiplied by 2 over the total number of students, which is 4. Okay, or you sum up all those numbers over 4. It's the same thing. In order to determine the standard deviation is the distance from the mean. Okay, how much the data are distributed around the mean. And in order to find the distance from from a certain data to the mean and log the variation over all the data, you need to put some square. Why? To avoid, like, if you have some data above and below the mean, and if they are equal distance and you sum up them together, you say that the standard deviation is equal to 0, which is not correct. There is a variation around the mean, right? So if we put a square for this one, this would become positive. Okay, and then we sum those together and divide them by n minus 1, by the total number of samples we have. Okay, let's take an example. If we have 2-inch round rods of the type of material is steel, okay, and this number 10, 30, the 10 here indicates carbon. We will be discuss this in the future, and 30 represent the percentage of the carbon in the steel, which is 0.3, and the type of manufacturing process, hot rolled. Okay, so you have a certain material that have been received for workpiece stock. 9 standard geometry tensile test specimen have been machined from random locations in various roads. In the test report, you have the ultimate tensile strength to be between 62 and 65, and you have only 2 rods. Between 65 and 68 megapascals, you have 2 rods as well. 68, 71, you have 3 rods, and 71, 74 kpsi, 2 rods. Okay, you are asked to find the mean and the standard deviation of the data. Okay, so the mean is equal 1 over n, the total number, which is 9, number of rods. So the total number of rods is 9. 63.5 multiplied by 2 rods, 66.5 over 2, and this must be equal to okay, you should be able to obtain this value. Okay, I don't have it. Now we want to determine the standard deviation of the data. The standard deviation, okay, you can use this formula, okay, is the summation of fi xi squared minus the distance from the mean squared over n minus 1 radical. Okay, so you calculate this term xi squared, okay, 63.5 square multiplied by 2 plus 66.5 square multiplied by 2 plus multiplied by 3 plus 72.5 multiplied by square multiplied by 2. So you can obtain this value. N xi squared, the total number is 9 multiplied by the mean, this value obtained here, okay, square, and then you can substitute and obtain the standard deviation. Let's take another example at which you need to calculate the mean and the standard deviation. So you have a fatigue test is performed on a rotating beam specimen. For each rotating cycle, the specimens experience tensile and compressive stresses at equal magnitudes. The cycle to failure, the number of cycles or rotations to fail, over 69 specimens are given in this table. So L represents the life cycle, okay, of the component, and the F is the frequency, how much component experience such kind of life cycle. So you have one component that experience 60 as a life cycle, one component 70, 3 components 80, 5 specimens 90. Okay, now we want to estimate the mean. So the mean, again, it is the summation of fi li over the total number of the specimens, which is 69. Okay, from I equal 1 to k. Okay, so we say 1 multiplied by 60 plus 1 multiplied by 70 plus 3 multiplied by 80 plus blah blah blah, 1 multiplied by 210 over the total number is 69, which is equal to 122.9 k cycles. So the average life cycle of the components of the 69 specimen is 122.9 k cycles. In order to obtain the standard deviation, you should be able to multiply 1 by 60 square plus 1 multiplied by 70 square, etc. So it is fi xi squared. Then you subtract it from the total number, n, multiplied by the mean square you obtained, 122.9 square, over 69 minus 1 and then radical, and you should verify this equal to 30.3 k cycles. All right. Now, because we are only testing a portion or a sample of the components, which is 69, it may not reflect the whole data sample or the whole manufacturing of specimens, and therefore this table is just a collection of a sample of the data, okay, some data. So if we plot this table, we see that it's not 100% normally distributed. But because we don't have a full understanding of the scenario and the situation of the real life scenario, we can assume it is normally distributed and perform our analysis. And later on, once we have a full understanding of the situation, we can determine which distribution best fit the scenario. For the time being, you assume it is normally distributed, and your objective now is to determine how many specimens are predicted to fail at less than 115 k cycles. Okay, so the objective is to determine for x less than 115 k cycles. Okay, so in order not to integrate, we can use the table by normalizing this value. Z is equal to 115 minus the mean that we obtained in previous part over the standard deviation, 30.3, which is equal to minus, okay, so this is equivalent to Z less than minus 2609. Okay, because Z is negative, return back to the table. Because Z is negative, we can directly take the value from the table as it is, alpha. So we have 0.2, 0.2, 0.2, let me write it down, 607. Okay, so we have on the table 0.26 and 0.27. In order to determine it accurately, it's important to copy those two. Okay, and we want to determine the value here in between, which is between 0.26 and 0.27. Okay, and then we need to determine the value here by interpolation. So I will be copying this 0.26. It has a probability of 0.3974, and the probability of 0.27 is 0.3936. Our objective is to find for the 0.2607, okay, in between. So from the table, we found out that 0.26 has a probability of 0.3974 and 0.27 with a probability of 0.3936. Now our objective is to determine the 0 point which is in between, 0.2609, and this is value x. Okay, now by interpolation we can say x minus 0.3974 over 0.3936 minus 0.3974 equal to the same way we subtracted the probabilities. We need to subtract the z-score, 0.2609 minus 0.26 over 0.27 minus 0.26. Okay, and you should be able to find x. You solve for x, and x is equal to 0.3971. Okay, so the probability of 0.2609, which is not included in the table, is found by interpolation to be 0.3971. Then the number of roads, so we have like 39.7% of the roads have a life cycle which is less than 115 k cycles. Okay, 0.3971 multiplied by 69 specimens, which is 227 specimens. Okay, so what is the reliability after calculating the mean, standard deviation, and finding the distribution and finding the probabilities, probability of a failure maybe? Okay, we say that the reliability is a statistical, if you want. The reliability is the complementary of the probability of failure. So it is a statistical measure of the statistical measure of the probability that a mechanical element will not fail. Okay, will not fail. So this is the probability of failure. So if we say that a component has a probability of 60% to fail, then it has a 40% not to fail. Okay, this is the reliability. If 1000 parts are manufactured with 6 parts failing, find the reliability. So we know that we have 6 out of 1000 will be fail. So it is 1 minus 6 out of 1000 will not fail. Okay, which is equal to 0.994, which is equal approximately 99.4%. If you have different components in the system and you want to find the total reliability of the system, then simply you multiply the reliability of each component. So if you have a shaft of a bearing with a reliability of 95% and one with 98%, you want to find the total reliability, just multiply those two reliabilities together, R1, R2, which is 0.95, 0.98, which is equal 0.93, with a total reliability of 93%. And to relate this to the design factor, we defined it as the strength over stress. In case we have a distribution, then you can find the average design factor by taking the average strength over the average stress. And therefore you have a margin of safety at which failure will occur. I mean, to avoid the regions of failure, this is the region at which failure will occur. Okay, the overlap between the strength and the stress. Our objective is to keep the stress less than the stress. And the margin for every value of stress and strength can be given by this. Correlating this to the reliability, we say that for a component to be reliable, the strength must be greater than the stress, or S minus stress greater than 0, or the margin of safety must be positive. So if we want to find the reliability, this is a probabilistic measure. So we need to say the reliability is the probability that S is greater than stress, or S minus stress is greater than 0, or the probability that the margin of safety is positive. So this is the end of the design part, at which we discussed various issues from the design process to the factor of safety, to in the design and safety is very important, to the economics, and in this session we discussed the reliability, so the component will not fail, how much the component is reliable. which is 1 minus the probability of failure. Okay. Of course, there are many other aspects that a designer must take into consideration, like the tolerances in the component and the codes, standards and codes, and many more. And we will discuss and elaborate on those on further sessions. But on the upcoming part, we will start with the material selection of the component. Thank you for watching.